And recording in progress. Okay, so um, welcome everyone. Zach is giving us part 2 today. So Zach.
Okay, so let's go ahead and remind ourselves of what we did last time. I won't do everything, of course, for lots of reasons, but the quick version of it is we introduced the idea of conditional expectation, which we accomplished through the use of Radon-Nikodym theorem for signed measures. One of the things this lets us do is define the conditional expectation of a function. So in general, we'll have at least 2 sigma algebras for our probability measure, call them sigma and f. And in those circumstances, if we have a random variable which is integrable, call it x, then f, the expected value or the conditional expectation of x relative to the sub-sigma algebra sigma, is a function. It is sigma measurable, and its major property is that if I pick any element of the sigma algebra sigma, then the integral of f, the expectation, with respect to the probability measure, is equal to the integral of x over the same set with respect to the probability measure. And it has a whole bunch of properties. We listed out 7 of them, and then Nathan added to it. These properties are actually useful to us, so I want to put them on your screen for at least a few minutes just so you remember some of them. In particular, we're going to be using Jensen's inequality today. We're going to be using the idea that these expectations are linear, so that would be part 3 there. We're going to use the property that if x is greater than or equal to 0 as a random variable, then the conditional expectation of x with respect to sigma is almost surely non-negative. Those are all going to be very big deals for us today. We're going to use them. Then we moved on to the idea of martingales. We introduced the notion of a finite martingale. So sometimes we'll call those martingales of length n. And so that means that you have a finite sequence of random variables, x1, x2, all the way through xn. And the property is that along with that, I have a filtration of sigma algebras, f1, which is a subset of f2, which is a subset of, etc. Let me go ahead and add the 2 here for posterity, so I look good looking back. And the property is that if I take the conditional expectation of any of the random variables xj with respect to the previous sigma algebra in the filtration, then the conditional expectation ought to be the previous random variable xj minus 1. Of course, you can go ahead and just define a martingale, an infinite martingale, which we typically just call martingale. And its property is that if you pick any value n in the natural numbers, then the n-length martingale created by restricting our attention to x1 through xn is itself a length n martingale. Everybody remember all this so far? Okay, I'm getting a thumbs up from Nathan, and I'm not hearing any outcry from the audience, so I'm going to call that a success for right now. We also gave a few examples here.
Hunter says no, but he wasn't here.
Who says no and they weren't here?
Hunter says no, but he wasn't here, so he doesn't get to complain.
That's true. Hunter, you are not considered for this. You are a second-class citizen right now. Okay, so we gave some examples. So, of course, if we find out that every single random variable that we have is equal to a constant, then, of course, we have a martingale. If you have a random variable x, and what you do is you produce a filtration, doesn't matter if it is an infinite or finite filtration of sigma algebras, then we can always define xj to be the jth conditional expectation of x, and that will produce a martingale. Actually, and I double-checked this today, this is kind of a nice example, because any martingale can be written that way. So if you just give me a general martingale, let's just say an infinite martingale like so, what I can do is I can choose x to be xj for any j or xn for any n. And then if I have this definition, then I can work through the definition of, I can work through the integrals and prove that this particular definition, along with the process in the example 1 right here, produces the self-same martingale that we had before. So this ends up being kind of a general notion of how we create martingales. We also had another example, which was if we have a martingale already, say xj or xn, doesn't really matter, with respect to a filtration f1, f2, etc. through f, and then we're also going to, and I should have mentioned this last time, we're also going to include that in this martingale sequence we have an x0. And what is x0? Well, x0 is going to be really easy. we already know that, and this is coming from our remark, if I have a martingale, the expected value of each random variable in the martingale sequence is going to be a constant c. It's going to be the same thing. So what I do is I simply define x naught to be the expected value of, say, x1. Doesn't really matter which one it is because it'll be equal to all the others. And if I make this definition include x naught as a part of our slightly adjusted martingale sequence, then I can create a brand new martingale sequence by defining y to be given by the difference of consecutive terms of our original martingale sequence x. Still seem pretty good? Okay, so let's go ahead and move on to the very first of the major results that we want to have for martingales. It's kind of a useful one, and it uses Jensen's inequality. In fact, actually, you can basically just prove this by mouthing the words Jensen's inequality for conditional expectation, and you're done. And this time, I'm going to be super, super awesome. I'm going to go ahead and paste the lemma directly from Varidan's book into the notes right here, and then just make it a little bit bigger. Okay, if I have a martingale, and I have a convex or a concave function phi with a property that phi of xn is integrable, then the sequence or the pair sequence phi of xn, fn is a sub or super martingale. Like I said, this is just a Jensen's inequality. You can literally go back to Jensen's inequality in our conditional expectation talk, and you'll be able to derive this directly from definitions of martingales. Is everybody comfortable with that, or do you want me to go ahead and actually prove it?
No, I don't need a proof. I just think, did you ever get the definition of sub or super martingale?
Ah, that's a good point. So let me go ahead and throw this in here. Varidan, this is actually one of the few places where I should go ahead and change things a bit from Varidan. Varidan is really great about the martingales, but he forgets to introduce sub and super martingales until a little later. I suppose it's not really fair to say he forgets. He defines them afterward. We say xn or xj, whatever you want to call it, is a sub or a super martingale. Actually, I'm going to go ahead and capitalize martingale in here just because it looks so much fun to have capitalization in the middle of a word. If equality in the martingale definition is replaced by one of the two inequalities. So in other words, if we go back up to our martingale definition back up here, it says that the conditional expectation of xj with respect to the previous sigma algebra and the filtration should be xj minus 1. Well, if we end up putting in if we say that the conditional expectation is less than or equal to xj minus 1, then we have a sub-martingale. If we replace it by greater than equal to xj minus 1, then we have a super martingale. Does that make sense? In those cases, we're not asking for quite as much, of course. I mean, you can tell that from the inequality. But the idea really with a martingale is that in average, anywhere, the terms, the random variables of our martingale sequence should behave more or less the same. And when we move to sub or super martingale, we're asking for the idea that when we compare our conditional expectations to the martingale sequence, there was a nice, easy relationship, a bounding relationship of some kind. Thank you for pointing that out to me. I knew I needed to make that definition, and for some reason, I already in my mind had it. Okay, so with that definition and with that lemma out of the way, making things pretty easy, we're going to go ahead and produce we're going to produce a remark, actually. I want to produce the remark by just copy and pasting it. So hopefully everybody is familiar with the fact that if I take absolute value and raise something to the power of p, for p greater than or equal to 1, we're talking about a convex function. Well, it turns out that using lemma 5.1, we can actually use the idea of absolute value raised to the p for martingales. So if I have a martingale xn fn, then the absolute value of xn raised to the p relative to the filtration fn is a submartingale, with the only caveat there being we need the expected value for xn to the p to be less than infinity. So they need to be LP functions. Everybody good with this idea too? All right, so let's have one of the very first inequalities that I encountered with Doob's name on it. I mentioned this one last time. So Doob's inequality, Theorem 5.2 invariant. Suppose that we have a martingale sequence of length n, then the probability of the set where the supremum of the xj random variables is greater than or equal to some value L is less than or equal to 1 over L, the integral over a set relative to, or I'm sorry, the integral of the absolute value of xn over the set, or in other words, you can just make it easy and say less than or equal to 1 over L, the integral of the absolute value of xn. I hinted at how this was proved last time. I'm going to prove it this time. It's pretty easy. So proof, and let me double check my notes just to make sure I don't lead you guys astray, because that's the last thing I want to do.
It looks just like to me Markov inequality, yeah. But maybe
Looks
there's a
like-
special property that it's scroll n, yeah. And that's why it's.
Say that again. Which property does it look like it is?
So it looks like Markov inequality, or is it? No, it's Markov, yeah. But it's
I'm
maybe
not-
the special thing is that it's since it's Martingale, you actually get it holds for all n. Maybe that's what the special. I'm trying to figure out how this is different from Markov inequality. I think it's because you actually do have. So why is the property of Martingale actually needed? Is my question.
So the property of martingale here, I think, is coming from directly, and I'll double check this just to make sure. But the property of martingale here is actually coming directly from this middle inequality here. You'll see it in a minute. But basically, the way that I'm going to prove it is going to utilize Chebyshev's inequality. It makes it pretty easy if you do it that way. You break everything down to these subsets, which are disjoint. You use Chebyshev's inequality on each of those sets because it makes things pretty easy. Then what you do is use martingale inequalities. And actually, you can use lemma 5.1 as part of it as well in order to move from talking about the random variable xj to talking about the random variable xn at each step. Then you're able to use sigma additive properties of the measure in order to get the right inequality here. Okay, so I kind of just summarized it, but I'll let you guys know what's going on. So what we're going to do is we're going to define S of omega to be equal to, and of course, since we've got a finite sequence here, we can call it the maximum of the absolute value of xj of omega, like this, like so. And from right there, let me double check what I'm writing here. Just want to make sure this is clear. When I say the set of omega is such that the supremum or the maximum, it doesn't really matter, of the absolute value of xj of omega, of course, I'm really talking about the set where S is greater than or equal to, be really handy if I made sure that I finished my set notation here, greater than equal to L. I'm really talking about the set where S is greater than or equal to L, like that. I'm actually going to move this down below because I'm going to make a definition out of it. And then from that definition, I'm going to implicitly define a whole bunch of sets that are going to be more useful to me in line with my design. Ooh, I rhymed. And that was almost a rhyme again because that's how cool I am, folks. Okay, so I want to call E this set here. This is the one that I'm really interested in. But of course, what we could do is we could break this up into a union. The union is going to be for j less than or equal to n. And the sets here are going to be, well, I'm going to eventually call them En. But the idea is that it's going to be of points omega such that the absolute value of x1 of omega is less than or equal to L, or strictly less than L, doesn't really matter. And this pattern continues until I get to the jth random variable. So in other words, EJ is going to be it's going to be the set that characterizes XJ is the very first time that we go above L. And I'll work in the implicit definition down here just to make sure the notes are clear. Okay, is it obvious to everybody that the sets EJ are disjoint? Okay, I'm getting a nod from Nathan. Nathan, is anybody else saying no? I'll laugh at them, but I will help them. I promise.
No one so far. So.
No one so far. Okay. Don't take the laughing at you thing too personally. Actually, I probably won't really laugh at you. I'll just help you instead.
We'll just go home and laugh.
Okay, so the collection of EJs is disjoint. And on top of that, if I take the probability of EJ, well, because of the way that I've set up the sets EJ by Chebyshev inequality, of course, what I can do is I can say that this is less than or equal to 1 over L, the integral over, well, actually, in this case, I think it's, I'm going to say E like this for right now, and then I'll revisit that in just a second. The absolute value of XJ and I'll write here Chebyshev just so everybody knows how I got it. Well, here's the thing. Because we're already working with a finite martingale, one of the properties of martingales that we just investigated came from lemma 5.1. And in lemma 5.1, we said if we have a convex function, then what we should end up finding is applying the convex function to our random variables produces a sub or a super martingale. Definitely absolute value is a convex function. So what we should end up finding from here is that because of martingale properties, because of lemma 5.1, instead I can change this inequality. Actually, I should go ahead and put this as EJ here. And I'll put instead of XJ, XN.
I see. So this is where it gets used. Okay.
Yep, that's exactly where it gets used. Well, now we already know that well, I guess I better come down here and say it. By sigma additivity, and additivity of domains, which I'm just going to write as AOD. When I do the probability of E, because it can be broken apart into the disjoint sets EJ, of course, I can change this into the sum of the probabilities of the sets EJ. And then using what we've got there, it ends up being just the integral 1 over L of E, absolute value of XN. And then if we allow our set E to be, well, expanded, dilated outward to the entire set omega, like so, we end up just getting absolute value of XN integrated over all of omega, which is nothing more or less than the expected value. Uh-oh. Oh, no, there we are. There we are. For a second, it looked like everything went away. Can everybody still see my screen?
Yeah, sorry. I had to go outside. It was too loud in the Marshall Center. So
okay.
I'm now somewhere quieter. And I think the internet cut for a second. But okay, I think everything's good. So
all right, I'm going to pause for a second, make sure everybody can see my screen, and then I'm going to make sure that there are no questions about this. It's a pretty straightforward proof. Okay. Was that somebody on your end, Nathan?
Yeah.
Yeah, Marshall Student Center is loud. Also, it's apparently filled with ants right now, or at least that's what they're saying on Reddit. So I don't know. Be safe.
There's a Marshall Center Reddit.
No, there's a USF Reddit.
Oh,
In fact, spoiler alert, you can find Joel on there.
So I've heard.
He's on there. He's pitching for USF instructors and so on. I've come across him a couple of times, but I lurk anonymously. Okay. We also have a corollary 5.3. I'm not going to prove it because it's a little bit more involved. It would take more time, and it involves some tools that, frankly, I have not come across, and I don't expect the vast majority of you have come across either. So,
Cauchy inequality, yeah? Is that Cauchy inequality?
I'm not sure if it is Cauchy inequality. That's a good question, though. There are actually, remind me to talk to you later, Nathan, because the Markov inequality you were talking about, Cauchy inequality, these sound like things I want to hear a little bit more about, because if I've missed them, I want to come back to them.
These are like analogs of theorems for real analysis, just from Martingales. You can say something a little bit stronger. But okay, cool.
I think you're probably right. Actually, a lot of times what you find out with Martingales is you can do blah, blah, blah thing, and hey, it's just a slightly better version of what we knew how to do with general real analysis. All right. Okay. And that actually leads us to the very last theorem I want to do with Martingales before we move on to stopping times, which is great for us time-wise, because that might mean we're able to actually finish everything. If not, I guess next time could just be a quick summary and then talk about Doob's optimal sampling theorem. Well, we'll see what goes on. And that's going to be the Doob decomposition theorem. So let me go ahead and find that in the PDF really quick, so that way I can bring it to you. Aha, here we go. One of the cool things about a lot of these theorems is that they're actually nowhere near as difficult as they sound. I know some folks who are at least passingly familiar with some of these properties, but don't particularly like them because they feel like it turns into black magic eventually, especially in some of the applications that I'm interested in. And I hear what they say because the first time I read a lot of this stuff, it seemed like black magic. But it turns out that lots of this stuff is actually really easy. And once you're looking at it from the right perspective, everything comes apart nicely. Okay, so kind of like how I said Doob's inequality was supposed to be kind of a niceness result. It's supposed to tell us how nicely behaved martingales have to be in order to be a martingale. Doob's decomposition theorem can also be thought of as a niceness theorem. It works on infinite martingales, although I'm going to go ahead and make this statement without providing any proof and without having gotten this from the book, so take it with a grain of salt. We can always look at it later. I'm going to go ahead and say Doob's inequality also works for infinite martingale sequences. It's couched in terms of finite, but I'm pretty sure it can work for infinite as well. It seems like an obvious, very trivial thing. In Doob decomposition theorem, we start with an infinite martingale, or actually sub-martingale sequence. And what we're claiming is that the martingale sequence xn can actually be decomposed into two pieces, a piece called yn and a piece called an. Yn is going to actually be a full martingale, unlike xn, which is a sub-martingale. An is going to be increasing. A1 is going to be 0. And A1n is going to be fn minus 1 measurable always. Moreover, xn always determines yn and an uniquely. Well, my first contribution here is going to be to cross out the symbol an. So many times we're going to wind up talking about sets and using the symbol A to talk about sets. I really don't want to continuously use A for sets and also for something else. I want this to be clear. So in the place of A, I'm going to be using the symbol Z here. I'm just going to kind of quickly replace it all here so you can see what I'm talking about. So wherever it says AN, you can mentally replace it with the ZN, and it means exactly the same thing. All right, so what are we going to do? How are we going to make this happen? Well, I'm going to attack this a little bit differently from the book. The book wants to establish it a certain way. It wants to establish a couple of properties first. I'm going to instead jump directly to the first definition that makes everything possible here, and I'm going to say define, not A. I just got through saying don't think about A. Define Z1 to just be the constantly zero function. and then define from there Zn to be given by, let me double check my definition here, the conditional expectation of xn minus xn minus 1 relative to the n minus 1th subsigma algebra, and then we subtract Zn minus 1 like this. Okay, so what does this do for us? Well, I actually know, we know that Xn is a sub-Martingale. So as a consequence, when I take the expected value of xn minus 1 with respect to the previous sigma algebra, it turns out that we can use a little bit of the linearity, and we can use a little bit of the linearity and the absolute value properties of conditional expectation to show that this is automatically greater than or equal to 0. And if we know that's true, from this, when I take Zn and I subtract from that Zn minus 1, all we're left with is the conditional expectation from our definition. And of course, that makes this greater than or equal to 0. So that takes care of property 3. It takes care of property 2. And then property 4 is basically baked directly into the definition of the function Zn. All of that's made really nice and really obvious right away. Now, define Yn to be Xn minus Zn. Well, already we can see kind of where this is going. The only thing that we really need to do once we make this definition is check to see if Yn is actually a martingale with respect to the filtration Fn. And so that's the very last thing we're going to do. And in this particular case, I'll go ahead and mention the filtration along with the random variables, just to make sure we're all clear on what's going on. Okay. So what we're going to do is the following. I take an integral with respect to some Fn minus 1 measurable set A of Yn. And I'm going to note that per the definition up above, that simply means that with respect to A, we're taking the integral of Xn minus Zn, like so. And then what I'm going to do is use one of our classic tricks, and I'm just going to break this apart by adding and subtracting. So I'm going to have Xn minus 1. Then I'm going to use linearity of integration, break it up, and I'm going to have Xn minus 1 minus Zn, like so. Everybody clear on what I'm doing so far? Okay, so I'm going to go ahead and note over here that An belonged to the n minus 1th sigma algebra, just so everybody's clear on what's happening with that. So because we have a, one second, sorry about that. What am I doing? Sorry, I have to double check my notes. Sorry, guys. This is one of those times where I should have been a little bit more prepared than I am right now and could not quite help it. Okay, we're going to try and wing this real quick. Shouldn't be too hard. All right, so because of the way that we've defined things, it turns out that when I take this integral right here, the integral with respect to a of xn minus 1, since a is fn minus 1 measurable, it's exactly the same thing as the integral with respect to a of zn minus, or excuse me, plus zn minus 1. And then we have this integral over a of xn minus 1 minus zn. So, and and if we combine those things together, we should get an integral of a. We should end up getting rid of the zn's, and we should just end up with an integral of xn minus 1, and then plus, based on my signage here, that. Well, what have we accomplished here? Well, what we've kind of accomplished here is a situation where we can kind of keep on going back to getting expected values. Actually, you know what? Let me make this even easier. I'm going to get rid of the parentheses here. I see what's going on. I just need to give my brain a few helpful slaps before it woke up. Okay, so we have an integral with respect to a of xn minus 1. On the other hand, we have an integral of zn minus 1, like this. And what we should be able to do then is we should be able to see pretty quickly and pretty easily, I think inductively at worst, that this right here is simply going to end up evaluating to 0? No.
No, so you want
yeah, I don't want that. I don't want that at all.
Of yn, yeah, and you want it to be yn minus 1.
Yeah, I think somehow.
Right now.
Oh, do I? I think somehow. I think I've messed up a sign somehow. You notice that I've wound up with. You'll notice that if I replace it parentheses for a second here, I've wound up with this, according to my notation. But I'm pretty sure that I've messed up a negative sign in here. I think that this is supposed to be a minus, because if it's a minus, then that literally is just yn minus 1.
Yeah.
So I'm not sure where I've messed up the sign, but I'm 100% certain that what ends up happening is we have a minus there. And if we have a minus there the way I claim we do, then what we should end up having is nothing more than the integral by definition of yn minus 1, like so, which is what we would need in order to have a martingale. My apologies for not knowing where I messed that up. Something in here is just not working out, and I'm not sure why. It's probably a very simple thing. All right. With this done, we have everything we need. We've defined Zn effectively. It is growing. It is equal to 0 for Z1. It is Fn minus 1 measurable. We have shown that Xn is equal to Yn plus Zn. And because of the way that we've done things, because of our definitions, we've ended up with something that is uniquely determined once we have Xn, with maybe the only caveat to that being it might be uniquely determined up to a set of measure 0, probability measure 0. Everybody comfortable with this? All right. Are there any questions so far before we move on to stopping times?
Not yet.
Okay. Now let's go ahead and talk about stopping times real quick. I'm going to advance my PDF just a little bit, make sure that I have everything I need. Looking at the time, my guess is that either we're going to just barely have time to talk about stopping times and Doob's optimal sampling theorem, or that what we're going to end up doing is meeting again. I'm going to try to make it so this is the last meeting. Okay. So in order to do stopping times, well, there is a more general setting for stopping times. You can simply make stopping times with respect to some kind of ordered set. Varadin actually does it this way, and he makes a more general idea of what it means when we're talking about stopping times. However, for our purposes, it's not very useful. For my purposes, it's not very useful. And you can kind of recover the original definition with a little bit of ingenuity if you start off here. So I'm going to start off with a random variable, which is mapping directly into the natural numbers union with 0 and infinity. So tau is going to map from our space into natural numbers together with 0 and infinity as concepts, is a stopping time with respect to the filtration of sigma algebras F1 subset equal to F2 subset equal to, etc., all the way up to whatever F happens to be. If for every n in the natural numbers, we have the set of all points where tau of omega is less than or equal to n belongs to the nth sigma algebra in the filtration. That's all it means to be a stopping time. So why do we take this to be the definition of a stopping time? Well, the idea is that basically a stopping time is only going to be useful to us in the sense of taking information that we currently have, only information from the current time, and using it to decide whether or not to stop. A stopping time in a gambling game, for example, might be representing the player's decision to stop. And so we have to restrict it this way in order to make sure that it's only really taking information and talking about information that belong to current time and the stuff that happened previously. It shouldn't be able to take information from later on in the sequence, just like we shouldn't be able to. Well, from this definition, we have some stopping times that are pretty easy to do. So the very first one, it's an exercise, but I think it's a simple enough exercise that I can just leave it to you guys. And it comes directly from the book. Tau, which is identically equal to some constant k, let's say in the natural numbers like that, is a stopping time. That one should be pretty easy to see. A slightly less obvious example of stopping time, and one that I actually will talk about really briefly, I won't do the full thing, is if F maps the natural numbers back into the natural numbers. Actually, I should go ahead and say natural numbers union 0, just to be completely on the up and up here. So if it maps natural numbers 0, infinity back into itself, is non-decreasing, and if f of, let's say, m is always greater than or equal to m, and tau is a stopping time. In fact, I'm just going to go ahead and abbreviate this here. Hopefully you guys are all comfortable with that. I'm just going to write an ST for a stopping time. Then tau prime, which we define to be f composed with tau, is a stopping time. Well, seeing that tau prime is a random variable isn't so bad. Seeing that's a random variable with respect to our overall sigma algebra is not so bad. The only thing is showing that this restriction property, which I'm just going to call star, actually turns out the way that we want. But even that isn't so bad. So if we start trying to take the preimage, so let's see, tau prime preimage of what do I want to say? The set 0, 1, etc., all the way up to n. Of course, what that means is I'm going to be talking about tau inverse of f inverse of the set, because that's just how compositions work. We know that. And if you pay attention to how f works, the preimage of f on the set is only going to turn out one of two ways. Either it's going to be empty, or it's going to basically look like an interval, not really an interval since we're talking about natural numbers, but like an interval of natural numbers decreasing down. So it'll either be empty, in which case it's obvious, or it's going to be something like 0, 1, all the way up to some number m like this. And we already know how this is going to work out. We simply take the preimage under tau. We're going to get something which is an element of the mth element of the filtration sigma algebras. And since we know that these are always increasing sigma algebras, we simply get the desired result. Everybody clear on this? Okay, fantastic. Those are two basic properties. There's actually also another really nice one that I want to mention as well. This is another very easy one, so I'll leave this to you guys to think about. So, example, if tau is a stopping time, then actually, I should go ahead and say, let's work with two stopping times here. If tau 1, tau 2 are stopping times, ooh, changes in grammar, then tau 1 upward wedge, tau 2, which I'm going to define to mean the maximum of tau 1 and tau 2, and also tau 1 v tau 2, which I'm going to define to mean the minimum of tau 1 and tau 2, are stopping times as well. And actually, the very first example and this very last example right here end up telling us something really interesting, which I'm going to put as a remark. A stopping time, tau, is always a limit of the increasing sequence of stopping times tau and k, like that. And I'm going to let k, of course, be going towards infinity. Do that, and it's pretty obvious and pretty natural that we're simply going to get stopping times that tend toward one big stopping time. Everybody comfortable with that? Okay. After those facts, we're ready to define what we're going to call the stopped sigma algebra. And so it's going to look a little bit like this. Definition. If F1 subset equal to F2 subset equal to, etc., through some common sigma algebra F is a filtration. Then, when I talk about F tau, the stopped sigma algebra, and I do claim this is a sigma algebra, I'm talking about a collection of sets A. A, of course, is always going to belong to F, the overarching sigma algebra in our filtration. And if I take A and I intersect it with the set of values where tau is less than or equal to n, the result should be a member of the nth sigma algebra in the filtration. In other words, it is a sigma algebra that we're building in order to make sure that the information we have available at time n or smaller than n is going to always belong to the nth sigma algebra. We have a natural way of talking about information over time. Everybody comfortable with this definition? Any questions so far? That's kind of a weird thing to throw out there. And I'm going to go ahead and throw an exercise for you guys while I'm waiting for questions. Okay. Sounds like a no. That's okay. The factor exercise that I'm throwing up here on the board is actually very useful. So if xn is a sequence of random variables, not necessarily a martingale, on, let's see, I'm going to go ahead and put the whole measure space here. That and then P. Then x tau of omega, the stopped sequence, which means in our case a sequence whose subscript depends upon tau and which is then evaluated at omega, is f of t measurable or f tau measurable on the set where tau is strictly finite. Okay. All right, looks like we have just a couple more minutes. So what I'm going to do is simply copy and paste Doob's optimal stopping theorem or optimal sampling theorem. It goes by both names in here. And I'm going to quickly summarize what it means since I'm saving myself a whole bunch of time. I would have loved to do the proof for you guys, but I think if you pick up a copy of Eridan's book, you'll find pretty quickly that it's actually not that bad a proof, even though the result itself sounds very intimidating. So the idea is, go ahead.
If you want to spend a minute or two talking about the proof too, we kind of had a couple of technical difficulties, so you can take a little time extra if you want.
Okay. I don't mind doing that. I can actually take a second and do that. So the point behind the optimal sampling theorem, I know it says optional stopping theorem here, but optimal sampling theorem is another name that you'll see thrown out there, is that basically we've already got a sigma algebra F tau, a stopped sigma algebra. We know a whole bunch of properties about martingales. So the question is, if I work with respect to stopped sigma algebras and stopped martingales, will we have a similar relationship? In other words, if I've got two stopping times, bounded stopping times, tau 1 and tau 2, and if I want to know what the conditional expectation of x tau 2 is with respect to the stopped sigma algebra F tau 1, will I wind up getting a relationship with x tau 1? And the answer is yes. Almost everywhere, the expectation equality holds up the way we would expect, which means we can continue to work with stopped martingales on a stopped sigma algebra in more or less the same way as we did with martingales. This would be really useful because if we're using the idea that stopping time in our case, we're working with gambling. Stopping time is the decision to quit. Your random variables are the output, your winnings or losses from each step of the process of playing a new round of the game. Then that means that we can continue to use these Martingale properties for you as we examine your case. And it still will work even if we throw in the stopping times and take into account the possibility you might just stop at any time. Would everybody like to see the proof?
A sketch if you want. You have time.
Okay, a sketch should be good enough. As we see today, since I haven't had as much time to do this as I really would like, I'm going to be subject to small mistakes. So we might as well just sketch it anyway. All right. So the very first thing that we need for our sketch, proof sketch, one. We only need to prove that the expected, the conditional expectation of xk, where k is a constant, with respect to the stopped sigma algebra f tau, is precisely the stopped martingale, provided tau is a stopping time, obviously, and tau is less than or equal to k. That sounds almost like that shouldn't lead to the same result, but in fact it does. What you can do is you can use, through some of our conditional expectation properties that we talked about last time, that you can take, and I'll put this down here just really quickly so you can see it, that you can take the conditional expectation of, say, xk with respect to the sigma algebra f tau 1, and you can expand it into nested conditional expectations. The first conditional expectation, the inner one, is just going to be of xk with respect to, oops, can't forget this part, with respect to f tau 2, and then we're going to take the expectation of that conditionally with respect to tau 1.
So this is just tower property, yeah?
Say again?
This is just tower property from before.
Yeah, I haven't heard it called that, but yeah, it's exactly what we had before. It's not too hard to see this is true. And so then what happens is, if you assume, or if you end up showing that this property right here holds up, then that together with this ends up giving you everything that you need. Oh, I should say here, we only need to prove with. Okay, so once we've established that you don't really need the full strength of the assumptions, you only need to work with the one and then use some of the tower properties that Nathan was mentioning. Then we can move on to bigger and better things. What we do is we say that A is going to be a member of the stopped sigma algebra, and we're going to observe that omega can always be written as a disjoint union of sets EJ or EN. I'm going to use the symbol EN here for now, where EN is going to be the set where tau is going to be equal to n, just exactly equal to it. Of course, this is a disjoint union. So that means we'll be able to use additivity of domains, kind of like we did before. And then from there, if I do an integral of A intersected with En, like this, of xk, well, then what I'm going to be able to do is I'm going to be able to show that this is equal to the integral same set, but with xk replaced by xn. Remember, in this case, when I say k here, I don't just mean a random index. I mean something that bounds tau from above. And so if I do that, I can definitely say for sure that I can replace it with xn like this. And then what I can do is use my properties of the set en in order to replace this by a intersected with en, and then xn to be replaced by tau, like so. Well, if I have that from a few simple integral equalities, then it turns out that when I take the integral with respect to a of xk, let me double check my notes here so I can complete the sketch by dignity, with some dignity, I guess I should say. We end up finding that you get exactly this result. And from there, everything is obvious. Not hard to prove. It sounds a lot more impressive than it is actually difficult. Okay. Anybody have any questions for me?
So maybe one just vague question. So it, at least in what you're doing, so your examples of martingales, how is optional stopping theorem used?
Okay, so the idea in what I'm working in is that ideally, if we're playing a game where we have some shape and we really want to exit the shape, because exiting the shape like so means that the game ends and somebody wins money. What we're really hoping is that the martingale, which is going to represent the amount of money that you kind of owe at any given point in the game process, starting at some point, I'm going to call it, instead of x naught, since we've been using x naught or x to refer to random variables, let's call this p naught. My hope is that the process of moving from one position to another is eventually going to end. Technically speaking, when I start playing a game, I don't know that my process of moving from one step to the other is going to result in me leaving the game boundary. If the game is set a property, it should happen with probability 1, but technically it might go on infinitely, and we may never actually end up exiting. So what happens then is the stopping time then represents the point at which we first exit the game board. And so we use then this optimal sampling theorem in order to say, hey, listen, because of the way we've done things, since we know that the conditional expectation with respect to, and I'm going to go back just a second to our fact here, the conditional expectation with respect to, where is it? Oh, I'm sorry, it was the remark up here. Since I know that my stopping time can be represented as an increasing sequence of stopping times, tau wedge k, then what I can do is I can just say, well, oh, okay, replace tau 1 and tau 2 by the full stopping time maybe and one of the tau wedge k stopping times that I produce along the way. And the optimal sampling theorem says my conditional expectation carries through, and as a consequence, so does my expected value. So that means that if I can exit, if I do exit the game, I can carry through properties on the boundary or outside of the boundary through to the value function at any point, in particular at the point where I started the game. Does that make sense? That's a good question. Any other questions?
Not for me, at least.
It seems like everybody else is okay. I'll give everybody else just a few more moments because I know sometimes people shuffle through their notes and go, oh, wait a second, this is something I wanted to ask last time. So we'll see. Actually, while you guys do that, I'm going to stare at my screen judgmentally and see if I can figure out where I changed signs incorrectly. Ugh. That is really, really frustrating. All right. Well, to me, Nathan, it sounds like we've basically run out of time and out of questions, unless you've got anything more you want from me.
I'm done. So this is the end of your talk sequence?
I think so. So I would have loved to have spent just a little bit more time in some senses, but we've really run out of material to talk about. The only other thing that I could talk about is stochastic games. And realistically, since I've already pointed out a couple times, you really need to have infinite product spaces to represent the possibility of never stopping moving around inside the shape, never exiting. It really doesn't make sense to continue unless we want to bring in Kolmogorov's infinite product space theorem. And that's not really for this talk.
Yeah, sure. So maybe we can bring that in later. The plan right now, well, first, let's thank our speaker.
Hooray. Please clap.
I can never find there's a reaction button that's clapping. I think it's that one. There we go. So I think the schedule now, next week, it's either going to be me or Alice. If Alice still wants to talk, I'll have to ask her. Then we have, so that's the 8th. The 15th, someone else is going to talk. Actually, Aziza, if you guys know Aziza, is going to be talking soon, I think. Her defense, I think, is the end of the month. So I think she's talking the 22nd.
Okay.
So we have 2 open slots. And I think one of them is Alice, one of them is probably going to be me. So that's the tentative plan for right now. And then maybe after that, Zach, if you want to talk about stochastic games, we can bring it back around.
I might be willing to do that. Definitely a little bit later is good for me because I've got to catch up with a bit of research. But if we've got, it sounds like we basically got the month of October planned.
Yeah.
So as long as I put my nose to the grindstone, we should be okay to continue with more talks from me, maybe some stochastic games, maybe in November.
Okay. So that sounds all good. All right. So let me stop the recording.